Okay, come on. We're done with whatever you guys are talking about. Okay, so proportions are used in probability all the time. Okay, so when we do an experiment, we are using proportions to find out. Okay, so a proportion is really when you have two ratios or you set two ratios equal to each other. So proportion is a ratio equal to an equivalent ratio. So when we talk about fractions, 1/2 is the same as 6/12. Those are ratios because they are equal to each other. Okay, 1/2 is the same as 6/12. Okay, this is just reduced down, but we can find out what the ratio of the population is, and we can extend that out to see how much population we have. And we're going to do an experiment like that today, just so you could kind of get the idea of the tagging, no tagging idea. Okay. So, couple things about proportions. I don't really care if you know these names, but I'm going to tell them to you just because I need to tell them to you. When you have this, I have to remember because I can't remember which one's which, just because I never use this. A and D.
Sorry.
Okay, so I think it's funny. Okay, these two, the first and last of those are called extremes. Okay. They're the smallest and the largest usually of the thing, of your proportion. These are called the means. And you notice I know a lot about that. Because didn't you just see how much I remembered it? Don't remember the means and extremes. I know they're called the means and extremes, but. And what we find out is if you multiply the extremes, they will equal the multiplication of the means. Okay, in any ratio, if you multiply the means, they will equal the extremes. But I call it cross multiplication. But cross multiplication only works with ratios or fractions. So it's when one fraction is equal to another fraction. That's when it only works. So if you take the top one with the bottom one on the other side of the equal signs, it will equal the top one with the bottom one on this. So the top times the bottom equals the top times the bottom on the opposite fractions. That's really the one way I look at it. So it makes a cross or an X. You want to call it an X, it makes an X when we do it. But it's termed cross multiplication loosely. Okay. It's actually called the means extremes property, but that just sounds way too theoretical and all that kind of stuff. Cross multiplication is very easy. I multiply the top times the bottom, and that equals the top times the bottom. As long as they're a ratio, and the ratio has to have the equal sign. Okay, this only works when you have two fractions that are equal to each other, or basically two ratios that are equal to one another. That's the only time cross multiplication works. Okay. But what that allows us to do, because of that, we can find an unknown number. Okay, so what we look at is we go take, so what we're going to do is we're going to take a sample of whatever we're doing toothpicks because I didn't know how to get rabbits or anything like that. But we're using toothpicks. And so we're going to take a sample out, and then we're going to find out, we're going to tag some of that sample. So we'll have a tagged to non-tagged amount, or tagged, we could do a tagged to total amount. And this is in our sample. We're gonna make that up, okay? So this is the first sample. We're gonna go out, we're gonna get some different animals, we're gonna tag them. And that's really what they do. And the total is how many we got in the sample. This is the total of the sample. And this is how many, so if we got, say, 40 toothpicks, 40 rabbits, and we tagged 20 of them, that would mean that, so if we got, what did I just say that? We had 40 rabbits.
40 total. So we tagged 20.
And we tagged 20. Then I should expect 1 to 2. That's our ratio. Okay. Our sample is 1 to 2. Then what we do is we can predict based on that when we look at how many, we can go out and make another collection. So the second sample, we collect and we look at the number of tagged to the total. Okay. And it helps us to find out where is it? We can figure out how many total should be in the population. Okay, capture recapture method. It's called the capture recapture method. That's what it's actually called. This is done all the time to predict populations of different animals. That's how they come up with them, because they can't count every one of them. Okay, so that's what we're looking at, and we can use the fact that the ratios should stay the same. Okay, and so we're looking at the ratios to see that they're the same. Okay, so that's what we're looking at. That will tell us what our bottom number is. If we come back and find out there's so many tagged that we got, then we're going to estimate how many that would be in the population. Okay, so that's what we're looking at for that. Okay. So we'll practice this with toothpicks. I'm going to give you a pile of toothpicks. You're going to pull some out.
We're going to eat them.
Well, you can if you want to. I'm sure that won't go down through your digestive system very, very well. Yeah.
We could just shred them down into like shavings or something.
Yeah.
Okay.
So you can use your own teeth to shake it.
So we're going to see how this works to count how many toothpicks are in a container.
After a break, right?
Oh yeah, go take a break.
Thanks, Matthew. You're the best. Yeah, I didn't
I feel so proud of myself. Okay, so from what I know,
Yes.
every 200 years or so, it goes up or down. So, or that's what we've figured out. And every 1,000 years or so, that group, so it goes up and down, but some years it's hotter than the colder years, the years that go cold. So the gradual numbers of that whole 1,000-year section is up.
Yes, and then it can go.
And then,
yeah.
so that is why it was hotter a million years ago. Or as you said, that's why it's hotter a million years ago.
Yeah.
It's not. Because we don't know exactly how many 100 years ago that is. So it's estimated that when it turns 2200, the temperature will start to go down.
Mm-hmm.
We don't know that for sure, but
Yes.
and it's also that 1,000-year part is also a guess because the farther back we go, the more mixed the dirt samples are.
That's true.
So so it's just assumed,
A lot of assuming.
Yeah.
Yes.
but
Excuse me.
we're pretty darn sure about that 200 thing.
Yes, that is pretty close, yeah.
How many of the toothpicks are used?
That's what I didn't tell you. You have to figure out how many there are in your container without counting them.
I mean, like, have you used them?
Have I used them?
Are they used?
No, none of them are used. None of them are used. That's what you
So
meant.
the 2000s to the 2100s are up, 1800s to 1900s are down, 16 to 1700s are up, 14 to 1500s are down, 12 to 1300s are up, and thousands to 1100s are down.
We could measure it by mass.
Mass of what?
We can count how many are there by the mass
That's for what?
of the toothpicks. We could if we measure.
If we make, or the weight, you mean?
The weight, yeah.
Mhm.
Weight.
Because mass is density.
Yeah, mass density, the weight.
I don't think we have a
you-
scale that
it-
goes on our curve.
Yeah, so, I mean, we could, if we had an accurate scale, we could measure the weight of this,
Toothpicks are already in.
and then we could find it pretty dang close, because, well, they have different sizes.
If I remember, we can also.
First, you'd have to do an experiment to see if they stay pretty consistent.
Oh, actually,
We could.
we could grab a bunch of these toothpicks, count out how many there are of the handful, and then have a scale, and then we count how many there are, and then divide the weight by the weight of all of them.
Or
Or,
this only works if they object, but we could just measure both sides. There's another thing I forgot to do, and what? Just do the math.
the Mark Rober thing, like the M&Ms.
No, there's another one. There's a different.
I'm gonna go get snacks. And go to the bathroom.
Grayson, how many are in there? Wild guess.